We now consider the solution of 2D, where we wish to find the distribution of S. From 2C, we found an expression for the moment-generating function of S, which we found to be finite on some neighborhood around 0. And there we got the expression like this. Now, in order to be able to recognize the moment-generating function for some distribution, it requires that we also think a bit about the distribution of S. Because the funny thing about S, if you think about how it is defined, is that it's given as the sum of ladder heights for I going from 1 up until k. Now, if there are no ladder heights, then S is equal to 0. Also, S is equal to 0 will imply that no ladder heights have been observed, because if you observe a ladder height, it will take a positive value with probability 1. Therefore, S is 0 with the same probability as k being 0. And recall that the probability of k being 0 was given as 1 minus lambda divided by theta c. So S has a positive point probability in 0. On the other hand, S has density on the rest of the positive half-axis because the ladder heights are exponentially distributed. That means, intuitively at least, that S follows a mixture distribution. When we try to rewrite the moment-generating function for S, we will therefore be on the lookout for an expression that looks kind of like this, and another term involving lambda divided by theta c, because we have a feeling that that is what we should be looking out for. So let us try to calculate a bit more on the moment-generating function here. This is equal to a fraction where in the denominator we have theta minus alpha multiplied by theta c minus lambda. And in the, did I say denominator? I think I wanted to say in the numerator. And in the denominator down here, you also have theta minus alpha multiplied by theta c. However, there is no minus lambda because what you have afterwards is you subtract a theta lambda. If we try to look at the terms that are in the denominator versus the numerator, then you see that these terms are actually very alike. And in the denominator, what you have apart from these terms is minus theta lambda, whereas in the numerator, you have minus theta lambda plus alpha lambda. So the difference between the numerator and the denominator is the plus alpha lambda that is in the numerator. Therefore, if we can just subtract alpha lambda, then what you get is actually that this expression is equal to this expression, and those two divided is equal to 1. However, we can't just subtract something without adding it again. So we get this. Now, this entire first part of the expression just gives us a 1. And after that, we get a fraction where you have alpha lambda on the top, and then on the bottom, you have something more. What do we have in the bottom? We have theta squared c minus alpha theta c minus theta lambda. And recall that we're pretty interested in trying to find some expression where lambda divided by theta c is there. So let us try and get some lambda out of this expression. So I can take this lambda out. And let us also try to get a theta c out of this expression. Well, if I take theta c out of each term in the denominator, what I get is theta minus alpha minus lambda divided by c, right? Now, can I do something with this? Well, yes, I can, because what I have is 1 plus lambda divided by theta c, and here I have alpha divided by theta minus alpha minus lambda divided by c. What can I do about that? Well, first of all, I can recognize that since alpha also appears in the denominator, what I actually have here is just theta minus lambda divided by c divided by theta minus alpha minus lambda c minus a 1. And the reason for that is because you can think of 1 as theta minus alpha minus lambda c divided by theta minus alpha minus lambda c. And then when you subtract that 1, then you subtract both the theta term and the minus lambda c term, and you just have a plus alpha term left. So that is probably useful enough to be a weird identity of some kind, but or else you can just think a little bit about this, pause the video and try and see if you get the same thing. Okay, this is equal to 1 plus lambda divided by theta c, and what do we have? Well, let's just take the minus 1 out already now. So this is 1 minus lambda divided by theta c plus lambda divided by theta c multiplied by lambda minus theta minus lambda divided by c divided by theta minus lambda divided by c minus alpha. Okay. And what we see here is this is the probability of k being equal to 0. And this is, well, the probability of k not being equal to 0. And what you have is actually the moment generating function of a mixture distribution. Where the moment generating function is equal to one with probability 1 minus lambda divided by theta c, and it is equal to theta minus lambda divided by c divided by theta minus lambda divided by c minus alpha with probability lambda divided by theta c. And what that means is that the probability distribution function of S can be written as the weighted sum of two distribution functions, where the first distribution function belongs to this moment generating function, and the second distribution function belongs to this moment generating function. So the weights of these two distributions are respectively 1 minus lambda divided by theta c, and lambda divided by theta c. Let's try to recognize this moment generating function. It is in fact the moment generating function for an exponential distribution with parameter theta minus lambda divided by c. And this probability distribution over here, well, that is just, this moment generating function is just the moment generating function for a stochastic variable that is equal to 0 almost surely, right? Because the mean value of e to the alpha 0 is equal to 1. So how do we write this up in a way that looks nice? Well, my recommendation would be something like this. It is the probability of x being smaller than equal to x, and then plus lambda divided by theta c multiplied the probability of z being smaller than equal to x, where x equals 0 almost surely, and z is exponentially distributed with parameter theta minus lambda divided by c. And if you want to write that up a little more nicely, well, then what you just get is that the probability that s is smaller than equal to x is given as 1 minus lambda divided by theta c, where since x is equal to 0 almost surely, this probability is just always equal to 1 as long as little x is greater than equal to 0. And then added to lambda divided by theta c multiplied by 1 minus e to the minus theta minus lambda divided by c x. And that is the distribution function of s.